Hello, this is a brief introduction and summary on practicing for your exam. Now, the first thing you need to do is, using the Physics SACE revision guide, is to take some stock take of your skills. There is no point in you revising and studying and making notes about content that you understand. All right? So you always focus on your weakness in order to improve your strengths. So do the little checklist here and be honest with yourself. If you don't know, then you say you don't know, and then you can actually work with your teacher or tutor and building up those areas. So at this time of the year, you should already have a plan. If not, make one. Make a little timetable and stick to it. All right? Flashcards also help you. Photos, so you can actually take photos of worked examples, and while you're on your phone board sitting on the couch, you can actually flick through those to actually keep those sort of solutions and notes fresh in your mind. Also, sticky notes decorate your room. It's a bit weird, however it is an effective technique. So put them on the back of your toilet, put them on your wall, put them on your mirror, so therefore you're always constantly being immersed. Concept maps, as indicated in the bottom left hand corner here, are a brilliant way and a proven effective way to actually help build the relationships and actually do understandings. And also, if you want to record yourself, so you can plug in some headphones on the way to school, on the bus, etc., and you can just listen to those. Likewise, you can actually get together with a group of fellow students and you can actually share them around. Alright, so make sure you follow the plan, stick to a schedule. Again, immersing yourself visual, auditory, and also making summary notes, but make sure they're concise, okay? You're not writing just to get hand exercise. Be mindful of your progress and how your sort of emotional welfare is going. Definitely stay off social media. It has been shown, if you listen to music, stay away from ones that actually have no lyrics in it, because then your subconscious isn't processing it. That's actually been researched. And if you do feel stressed and you need to take a break and do some exercise, that's been shown to actually effectively reduce stress levels and increase blood flow to the brain, and release a few endorphins, and it actually will, after a bout of exercise, you can actually revise a little bit better. Okay, practice doesn't make perfect, however practice does allow you to find patterns. Okay, and any merit student will say, oh yeah, you know, this is this particular question type, so that's what you're doing, practicing to find patterns. All right. And of course, the more practice you do, the more likely you'll see patterns. So when you're actually given a bit of a curveball, you can go, oh yeah, that question's like this one. Make sure your responses are concise, look at the mark scheme, etc. Don't write half a page for 1 mark. Speed in your response, you only got 2 hours, okay? And don't practice items that you already know. Common mistakes. Alright, so when you get a question, you get the equation, you rearrange it, you substitute and you solve. That's what you need to do. Alright, so show those 4 steps in all of your solutions. Do not explain concepts using equations. That's just not going to fly with exam markers. Do not use the equation solver. So for you mathematics students out there, stay away from it. Make sure you check your data entry. So many times you actually look at students' work, they've got the correct working out, but then they've actually entered it incorrectly in the calculator. Don't be afraid to use brackets. And some of these questions require squared numbers, and sometimes it doesn't. Make sure you square the numbers. All right. That is a very common mistake. Students write it down, but then they don't type it in their calculator. Diagrams must always have values. Also, with your vectors, make sure you put it in the direction of. All right. Another way can be in and out of the page, especially when it comes to magnetic fields or electric fields. And also when you're adding different directions, okay, make sure there's a subtraction. If they're in the same direction, put them as an addition. I mean, that's a stage 1 problem. However, students made that mistake in last year's exam, so please be aware of it. Alright, so now you can watch the 2021 exam as I go through all the steps, and I do give out little hints and problems that students had last year. It goes for an hour, however, just look through it, practice it. Feel free to fast forward to questions that are the harder ones, the ones you understand. Alright, just skip them. Alright, thank you. Okay, so here we have the typical two-dimensional projectile motion, and that is the vertical velocity. We'll have the horizontal velocity here. That one is opposite, so we'll be using the sine function on that one. And this one is adjacent, so we'll be using the cos function on this one. Show that the initial vertical speed was 6.88 meters per second. So sine of 35 degrees is going to equal the vertical velocity divided by the hypotenuse, which is 12.01. Notably 3 sig figures, including the angle there. Alright, so that's divide by over here, so on the other side will be times by, so 12.0 times by sine of 35 is going to equal the vertical velocity, which actually, when you round it all off, equals 6.88 meters per second. Don't forget the units. Show that the ball reached the maximum height after that amount of time. So velocity equals initial velocity plus acceleration times time. Again, write the equation, rearrange if necessary, and then substitute and calculate. So that's a positive, so on the other side it will be negative. That's a times, so on the other side will be divide. So let's plug in our numbers here. 0 minus 6.88 divided by negative 9.8, because it is acting downwards, and that will be equal our time, and that will be 0.702 seconds. Don't forget the units. Determine the maximum height that the ball reached. Alright, so I'm not going to use one that uses time. So velocity squared minus initial velocity squared equals 2as. Now the initial velocity is final velocity at the zenith is 0, so we can actually cancel that out. So minus v squared initial velocity squared, that's times by, so on the other side it will be divide by. And let's substitute our values. Minus 6.88 squared divided by 2 times negative 9.8 equals our displacement, which equals 2.42 meters. Alright. The most common mistake last year was that they didn't get the negatives correct, and therefore they ended up with a negative distance, which doesn't make any sense, because that means when they kicked the ball upwards it actually went below the ground level. Okay, explain the effect of air resistance on the maximum height reached by the ball. Alright, so you're going to kick the ball there. It's going to, as the ball's going upwards, it's going to hit the air, so it's going to gain another extra force opposing its motion, and we've also got gravity. If you wrote down something about range, then that's not worth any marks, because it clearly says what is the maximum height, nothing to do with range. So there's going to be a decrease in the maximum height. Please note I'm actually writing this in note form. Do not write that style for your final exam, because you'll lose marks. Alright, so there's going to be a decrease in the maximum height. So we've described what's going to occur, and now we have to explain. A lot of students always forget the explanation. Though they can describe the result, you need to explain why. So here I've said the maximum height is decrease. The force vertically decelerates the ball in addition to gravity, and that also decreases the time of flight. That's the TOF. Or there's actually less vertical velocity to obtain a maximum height. Alright, so what we have here is an electric field basically between two plates. A lot of students were unable to do the first question, where we actually need to sketch the electric field lines between the ground and the base. Now these are parallel, so therefore the electric field distribution is going to be even. Now how do we know that? Or how are we going to represent that? We're going to make sure that the spacing is even. Okay, and if you're not artistic, you can actually leave a note for the marker and actually say evenly spaced. And also it'd be good if you indicated right angles to the surface. Alright. And don't forget, you need to put in the direction in which a positive charge would actually flow. This type of question is technically a stage 1, so everyone should know this one. However, people last year did stuff it up. Okay. Potential difference between the ground and the base is 1 gigavolts. A lot of students forgot about the giga and actually just put in 1 volt there, or 1000 volts. So make sure you use your prefixes correctly. So the electric field is the change in voltage, or the potential difference over the difference there. So equation, let's substitute values now. So there's your 1 gigavolt. There's your distance, which is indicated in the diagram there. Grab your calculator. Don't forget your units. So now it says calculate the magnitude of electric force. Key word there is magnitude. So the electric field is the amount of force per unit charge. If we actually rearrange that, so electric field is equal to, if we rearrange that, that's going to be force is equal to the electric field times by the charge. Alright, now we've got our equation, let's substitute our values. Now that is a very small force, is what we expect anyway, because it's only on an electron, which has very little mass, etc., and very little charge, I should say. Okay, let's look at this one here. Believe it or not, this is a very old question. It's very popular about 10-15 years ago. Alright, so we've got a current going upwards. So automatically I'm going to go for the right hand rule. So the thumb is going to go in the direction on the wire there, and the magnetic field is going to be circular. Now a lot of students mess this up, because when they were describing the magnetic field at point X there, they actually said clockwise or anti-clockwise. Well, no. This symbolic diagram here is actually representing the X plane. So really it's going into the page, and this one is actually coming out of the page. So you would actually use a little dot to represent it coming out of the page and an X going into the page, which coincidentally is the same as the question. Alright, so show that the magnitude at that field is at that amount there. So let's grab our equation, magnetic field. Alright, so now we actually substitute our values. And of course, don't forget the units. Alright, state the direction of the magnetic field at X there. Okay, so what we need to be saying is actually into the page. Alright, so now that we've done all those magnetic field calculations, we're going to introduce the charge and examine the force there. So the first part here is actually calculate the magnitude of the force acting on the proton. Alright, so force is equal to QVB. Let's substitute our values. We've got 3 sig figures here, because in the question we've actually got 3 sig figures. Though it could be argued that here we've actually got only 2 sig figures, so 1.5 times 10 to the power minus 2 newtons. Okay, state the direction of force on the proton acting due to the magnetic field there. Alright, so what we have here is remember, we've got a magnetic field going around here. This is going into the page. That one's coming out of the page. Now this proton, when it's moving, represents a current in a wire. Okay, it's just no wire. So using the right-hand rule, the magnetic field that's coming around the proton there, so that would be coming out of the page on the left-hand side, and it'd be going into the page on the right hand side. Now those are 2 opposite magnetic fields, and just like a north and south of the magnet, they're going to be attracted. Alright, so state the direction of the force. Okay, so it would be towards the wire. Okay, so always when you're putting in a direction, make it refer back to the object that it's being attracted to. Okay, so here we have the emission spectra from absorption spectra from the chromosphere on the Sun, and our Sun is a recycled one, so it's actually made up of bits and pieces from other matter, so it's not a brand new one. So there will be other elements, and again helium was discovered on the Sun before it was actually discovered on Earth. So let's actually have a look at this one. So that matches up with this one, and we also have this one matching up with this one, and also this one matches up with this one. We cannot use this one here because it actually appears on both. Alright, the fact that these are absent on the iron just gives us enough evidence to say, yes, it's actually krypton. Alright, so we've actually done that. Alright, now it's a little bit hard to explain this one, so there is no harm in actually referring to the diagram. Okay, so here I'm going to write the following. Okay, so here the emission spectra are circled, so you might want to actually refer back to the diagram to help your explanation. But please note, it's only worth 2 marks, don't write half a page. Okay, so we've got the cyclotron. Magnetic field just keeps it going around, and the only place that's going to make the particles go faster is actually across the D's. So work is equal to Q delta V. Let's substitute our values now. And don't forget the units. Okay, so the next one, a little bit complicated. So we will need to do some rearranging. So here we've got the kinetic energy and we've got the length there. A lot of students make a mistake with this particular question simply for the fact that they don't enter it correctly in the calculator. Alright, so let's start with this one. So let's get our equation down. So this is divide by, so on the other side it's going to be times by, so. And we're going to take this part here and put it on top of there. If you have trouble with rearranging, don't forget you've got that triangle system. Have a chat with your teacher, they can explain it to you in more detail how to use that little cheat there. Now we've got our equations all rearranged, let's substitute our values. So we've got if I was going to enter this on the calculator, I would actually include 2 more sets of brackets. And that way you're going to have less errors, okay? And that will give us the answer of... Again, this is where students messed up on this particular question. Simply data entry on the calculator. We have got we've got Mars, we've got Magellan going around it, fantastic. We are given the masses, so let's work out the force between them. And it says magnitude. So force equals gravitational constants, the little mass of Magellan, the big mass of Mars, over the radius squared. Most common mistake with this one is actually forgetting the r squared value there when they're actually entering into the calculator. Alright, let's substitute our values now. So what we have here is we've got this, that is 4 sig figures, so we will need to change that down to 3 sig figures. So the force is going to be 15, 10, and don't forget the units. Now the other mistake that students made with this one is here we've got kilometers, so I've times it by 1,000 there. So a lot of students actually miss that one there. So please pay attention to the units or any prefixes on the units to make sure you have the right quantity. Alright, so this one actually a lot of students stuffed up as well. They just said, you know, force of action equals opposite reaction. That's some sort of bad movie line. So again, you give an answer and then you actually have to explain it. So you'd need to actually say that the force of the Mars is going to be equal and opposite on the force on Magellan, and also the gravitational forces are attractive, so mutually attractive. When we see an elliptical object, we are going to automatically think of Magellan. Alright, so we've got point A to point B, and then we've also got point B to point A. Alright, using one of Kepler's laws, explain. Okay, so we're going to actually have to put which law are we going to be looking at when the time from point A to B is going to be shorter than B to A. So we all know that it slingshots around, it speeds up, and then it slows down over on the other side. We need to explain why. So which law are we looking at? So we're looking at Kepler's second law. Now we need to explain this one here. So if we're looking at the section A to B, that's the area that it sweeps. If we're looking at the section from B to A, alright, so that's this section over here. That area is far bigger than this one here. So what we're going to say is that the area is also equivalent to the time. Right, so the area of AB is much less than the area going from B to A. So therefore there is a lot less time for the object to go from the section from A to B. Alright, so that would have given you 1 mark, and then actually describing it would have actually given you the other 2 marks. Alright, so here we have the tiltron tube. So more or less we're shooting electrons into a uniform magnetic field. We know it's uniform because you can actually see the magnetic field going into the page and equally spaced. Alright, so what's going to happen here is that there is going to be a force acting all the time in that direction. And that's always going to be perpendicular to its motion. So explain why the electrons undergo uniform circular motion when in the magnetic field. Well, the force is always going to be mutually perpendicular. So 2 key terms there, to the motion. And this is going to be acting radially inwards. So just like if you had a tether, okay, this is acting inwards, and that results in centripetal acceleration, hence the circular path. Alright, so now we've actually got some values here. So we've got magnetic field, and a key thing that students always forget is that it's in millitesla, so again don't forget about the prefixes. Alright, so R is equal to the momentum over charge times magnetic field. Alright, so that's divide by, so on the other side will be times by. And that's times by, so on the other side it will be divide by. Let's now substitute our values. Again, that mass will be, the mass here will be on the equation sheet, and that will give us a velocity 3.86 times 10 power 7 meters per second. If you get a value that's over 8, well 3 times 10 to the power of 8, then you're going faster than speed of light. So you must be aware that you've made a mistake somewhere. So always double check for realistic answers. Okay, so the next one, we've got the tether ball, and a lot of students did not do well on this last year. So more or less you're going to, when the ball was struck, okay, the speed of the ball continuously changed as the rope unwound from the pole. Alright, so what would you investigate with this design practical? So let's have a look at 2 variables that you could do to alter this. Now, the best ones here will be, the force. So how hard you actually hit it. So that's a good one. And also the mass of the ball. Alright. because that will affect its motion, momentum, etc. You could also look at the angle you hit the ball at, and you could also look at air resistance. But again, that's going to be fairly hard to actually design a practical around using, you know, the technology you've got around. So I'll be picking on those two. So design a method to investigate one of the variables that you did in part A. So the first mark would probably be on first you've got to do your independent and dependent variable. Alright, and also look at your constants. Second part would be a method. So again, depending on what you actually chose. And another one, so that'd probably be worth 1 mark. That would be about 2 marks. And then you'd actually be, so you'd actually look at your results. Now you're not actually conducting the results, however, having a nice organized table of your independent variable, okay, and the forces that you might want to choose. So let's say you're doing force, you do 1, 2, 3, 4 newtons, and then you would actually have your dependent variable here, and you just, again, there would be no data. So that would be a mark there, and of course another mark for outlining your constants there. Alright, a lot of students actually tried to substitute values in there and actually come to a conclusion, etc. However, reading the question here is that what method. Alright, so you're not looking at examining any results and coming up with a conclusion, etc. So that was a common mistake last year. Alright, so what we have here is the SHE question, and students did this quite poorly as well. The space company that launches and operates satellites, this company satellites global images, so that's a key terms, and high resolution is another key term, so therefore there's some sort of advantage with this technology. Also collected each hour, and they're not affected by smoke or air pollution. So again, we've got some sort of development there. Images transmitted to Earth as EM waves. This allows scientists to constantly monitor the Earth. So that's a very important one. Environmental challenges. Okay, with some examples there. Is part of the SpaceNet partnership, and that provides satellite imagery for researchers, developers, conservation, security services, and mapping. Okay, now the most common mistake is that students will actually describe what the SHE aspects are. Alright, so using our little acronym here, we've got CC for collaboration communication, D for development, I for influence, and A and L for application limitation. So CC dial. So if you forget, you can use that acronym to remember. Alright, so communication and collaboration. Again, we're looking at environmental, fires, agriculture, and also part of the SpaceNet. So these all require working across different industries and different types of people, and they need to feed that data in and actually respond to any imagery concerns. In terms of the development, okay, so they've improved the resolution of the images, they've improved transmission and also communications technology. So that's another aspect. Influence, working with conservationists, so actually to bring about change, improve the ecosystems, etc. Alright, influence, so now we can actually have better security, people live better, and also mapping, very important there, and also making sure that the space industry actually grows. Hence South Australia, we actually are supposed to be the hub for Australia. Application limitations. There's still some work to be done on image quality due to atmospheric conditions, so nothing's perfect. However, they're working on it, and of course if that image quality is quite poor, then the amount of information you receive is reduced and your decision making process is actually influenced. So again, do not discuss what communication and collaboration is. Actually explain what the communication and collaboration will be, what examples of what is actually occurring. Refer back to the article, okay? Do not refer back to the SACE descriptions of what the CC dial aspects of the SHE are. Alright, so we've got a nice circular orbit there. So there's the space station, or the monitoring satellite there. Okay, so let's get on with this one here. Radius is equal to square root of GM over R. So let's substitute our values now. Okay, so now we're actually going to put in radius. However, please don't forget about that's from the surface of the Earth, and we need to know the radius from the Earth. So that will be found on your equation sheet. So that is one of the most common mistakes. Students forget that one, and don't forget the square roots. So the other common mistake with this particular question is, again, not entering into the calculator correctly. So velocity is going to be 7613 meters per second, but we only want 3 sig figures, so that will be 7610 meters per second. Calculate the orbital period. So period is equal to 2 pi r over v. So let's substitute our values in. So 2 pi r, which is equal to that 4.99 times 10 to the power 5. Don't forget about the radius of the Earth. And that will give us 5670, and that's actually at 3 sig figures. And don't forget the units, which is in seconds. Alright, so we've got an emission spectra here. So the electron transitions down, and the bigger the transition, the higher the frequency. So the bigger the transition, higher the frequency. The smaller the transition, the lower the frequency. So we're heading to the reds. So to look at this one for a small transition, okay, rather than 3 going to 1, we've got 3 going to 2. That's going to be the highest one, so it's actually going to be D. And that one has the lowest energy transition. And we can also say that the energy is actually inversely proportional to the wavelength. Okay, hence determine the energy of photons that are produced when electrons transition from N3 to N2. That's fine. So we've got energy is equal to HF, and C is equal to frequency times wavelength, which is the wave equation. So frequency is equal to C over the wavelength. Substitute that back in, so E is equal to HC over the wavelength. So let's actually substitute our values now. And don't forget the units. Okay, so we've got these mobile phone chargers, one of the most inefficient types of technology. You get a lot less wastage if you just plug the phone in to charge. So here we're actually, this setup here is actually a solenoid. So this one here is your primary, and then this is going to be your secondary. Alright, so more or less this is going to produce an alternating magnetic flux, and that will make this coil here produce a magnetic flux which opposes the one that's being generated here at the primary. And of course, if that's producing an opposing magnetic flux, then it's actually going to induce current in that coil, which then charges the phone. So here the alternating current produces an alternating magnetic field in the primary. The secondary, which is the receiving coil, produces an opposing magnetic field in the primary, or oppose the primary one. Of course, that's because we need to do some work, and that current induced, and the current is induced into the secondary to produce this field. Okay, so you want 3 marks or 3 significant points because that's what's the mark scheme. Okay, so explain why the EMF decreases when the phone is placed further away. Well, the magnetic flux actually gets weaker. So therefore, if the magnetic flux is getting weaker, then the amount of current that's going to be induced is also going to decrease. Okay, so lasers produced by the stimulated emission to produce light. So what we need to do is compare stimulated emission to spontaneous emission. Now, believe it or not, this is actually quite old question, so it's been recycled, slight twist on it. So again, paying attention to your revision guide and doing extra questions in preparation, going over past exam papers is always going to be a great help. So with with normal emission, you provide energy, excites the electrons. The electrons don't hang around very long at the excited state. They drop down and produce light. However, with stimulated emission, okay, then you want it to hang around in the metastable state for a bit longer, so you need specific elements for that. Not every element can do that. And then you're waiting for another photon to kick it off down an energy level to produce a photon as well. And don't forget that photon is going to be synchronized, so it's going to be the same phase and also in the same direction. So there's the similarities. Alright, so the key things here is that you are looking at the wavelengths produced, the direction and the phase. When you have got it lasing, then all of those 3 are going to be the same. However, when you've got just a spontaneous emission, okay, the direction and phase are actually going to be random. Okay, so now we're actually looking at a transition here. We actually have the energy transition. So a lot of students always forget, you know, EV, you actually need to convert that into joules if you're going to be doing any calculations. So what we have here is the energy is going to be equal to the 2 electron volts times it by the energy of 1 electron volt, and that's going to give us 3.2 times 10 power minus 19 joules. Okay, so E equals HF, which can also be written as F is equal to E on H. Now you've got your equation, substitute your values. So frequency, equals 4.83 times 10 to the power of 14 hertz. Now I can see that there's 2 sig figures here, 3 sig figures there, so I'd be saying that this is 4.8 times 10 to the power of 14 hertz. Okay, and it doesn't hurt to actually say 2 sig figures. Alrighty. Now we've got X-rays. So again, X-rays are going to see through things. Fairly straightforward. They're going to be attenuated depending on the different types of material. Now the first question here actually says, right, explain why X-ray spectrum for an X-ray has a maximum frequency. Well, the energy of the wave is actually proportional to the frequency, and you can't dump an infinite amount of energy into an X-ray machine, otherwise it blows up. Okay, so there are limits based upon the energy that you put into it, so you need to summarize that into a good argument, and that's going to be 3 marks, so you do need to mention a few details. On the last point here, I've actually mentioned that even though the electron has a certain amount of energy, you're not going to lose all of that energy into a photon because of the breaking radiation. So it's going to be on a scale from, 0% to 100%. So that's another factor as well, which depends on the actual material, which is the target that you're shooting the electrons on. Okay, so now we've actually got a calculation to chuck in here. So the frequency is equal to the work, which is equal to Q times V over the Planck's constant. Substitute our values. Okay, so don't forget the units. Alright, so we've got an image here and it says state one adjustment you could make to the X-ray tube to produce a clearer image. The contents of the container justify your answer. Well, an easy way to think of this one, if I want to see the contents better, then I'll shine more light on it. So what can we do to an X-ray generator to actually shoot out more X-rays, make it brighter? Well, that's to increase the filament current, so there's actually more electrons sitting on the surface, which can be then accelerated by the potential difference. Okay, so we've got the work function here. Now, typical one here. First one says, what is the first threshold frequency? Now, students seem to get a little bit slack when they come to this one. That here is clearly 8.5, okay? 8.75 would be sitting there, but you can actually see it's sitting a little bit further to the right. So I would be saying that this is going to be 8.8, alright? Whereas this one here, right, is going to be 8.75. So don't just scribble any answer that you think will fit. Alright, make sure you look at that. And don't put this into a calculator and try and get your calculator to solve where the x-intercept is. Okay, so that's another error that examiners will pick up on. So 8.8 times 10 to the power of 14, and don't forget the units, hertz. Okay, so don't forget that little bit there too, which is another common mistake. Alright, Next one, what's the work function in terms on electron voltage? So that means going to work it out in joules and then change the joules into electron volts. So E equals HF, substitute our values. Okay, so now I need to divide that by the amount of joules in 1 electron volt. So the energy is going to be 3.65 electron volts. Alright, so in the part B here, we're actually comparing that value that we just got with the quoted value. Now they're extremely close, and again the value that we got from the graph was one that we estimated, so it's not precise. So I would actually say yes, okay, and it's actually close to true. Alright, so 2 marks here, yes or no, and an explanation. Alright. True value means about accuracy. Alright. Just don't change the word true to close to a precise value, okay? Because that's going to be that's not what we're looking at. We're looking at accuracy. Don't confuse the two. Alright, the students on light onto here, so they've got a different frequency. Onto magnesium surface area, calculate the maximum kinetic energy that was emitted by that. Alright, so what we have here is the kinetic energy is going to be equal to, HF, which is the energy minus the work function. So the work function is to get it to the surface, and whatever's left over is going to be dropped onto the kinetic energy. Alright, so let's actually substitute our values in. So after rounding off, we've got 4.77 times 10 power minus 19 joules. Don't forget the units. Okay, so this is a classic question. So we've got a particle that's sitting over here, and we've got 2 forces acting upon it from this charge and also this charge. Notice how all the forces are positive, so they're going to be all repulsion ones, and so that will come up a bit later on when it does the vector diagrams. Okay, so show the magnitude of the electric force on Q1 to Q2 is equal to that value. Alright, so let's get our equation. That question was fairly straightforward. Using proportionality. So that means they don't want to see any equations. Okay. So let's have a look at the charge ratio. So the charge ratio is going to be 5.2 over 2.1. So that means it's going to be times by a factor of 2. Alright. So if you double the charge, then you double the force. However, with distance, it is actually an inverse squared proportionality. So what we have here is, what is the change in the distance? Well, if we go back up to here, that and that has a ratio of 4 to 1. Alright, so 3's into 12 go 4 times. So if I quickly whack that in, that means it's going to increase by a factor of 16. So now I've got my two quantities there. So 0.067 from the previous question times by 2 times by the 16, then that's going, after rounding off, that's going to be my 2.1 newtons. Alright, and that one is the two sig figures. Alright, so determine the magnitude and direction. Okay, so what we have here is 0.067 pushing that way, and we've got 2.1 newtons pushing that way. So again, they're opposite values. So 2.1 minus 0.067 is going to equal to 2.033, or just 2.0 if we're doing it to two secant figures. Alright, so that's the newtons. Now don't forget the direction. So it's going to be towards, okay, Q1. Alright. A lot of students always forget to put that in. Now this question here is actually a classic one as well, so you'll see this repeated over many years. A lot of students get stuck on this one because instead of actually having quantities, they've actually got values there. Alright, so puck A has a mass of 2m and puck B has a mass of m. Alright, so let's have a look at this. Now, it's actually for each time interval, it's moving that distance. Okay, so that can actually be considered to be the velocity. Alright, distance over time, there's the distance, and that's the time frame. So you're seeing multiple ones there. Now when I compare that to puck B, alright, so that to that is going to be the same one. So that means they're travelling both at the same velocity. So the momentum of puck A can be represented as 2mv, and puck B can be represented by, so momentum of A is 2mv, the momentum of puck B is going to be just mv. Alright. So on the diagram above, draw and label vector diagrams that represent the momentum of A and B before the collision, and then A and B after the collision. Alright, so let's have a look here. This has a mass now, which is equal to 3m. Okay, and that is looking very close to 2 squares there. It's a little bit under, but we're not too fussed about that one. What you could do is actually go, right, that is the momentum of A, and that's going to be the momentum of B. Sorry, that's the, yes, that's the momentum of A, that's the momentum of B. So that's going to be the 2 there, and if I actually join the dots, you can actually see that it's travelling in the same direction. Alright. I would personally get a ruler out and actually measure that. Alright. Or if you, now, I would not be going for the calculations, but if you wanted to do it, it would be mv squared plus 2mv squared, and then working out the square root, grabbing a bit of Pythagoras. So that would be mv squared plus 4mv squared, which would then be 5mv squared, then do the square root of it, so that will be the square root of 5 mass times velocity. Okay, so that would be the momentum of particles A plus NB. But again, measure that off of that. I can't really do that when I'm sitting on a computer here. Alright, so determine whether or not the momentum was conserved during the collision. So momentum was conserved. The direction was verified. So if the momentum wasn't conserved, that would be shooting off at a different angle. Okay, so we're doing some diffraction grading here. Okay, so calculate the wavelength of the helium neon laser. So what is your distances here? So you've been given 2, so they always ask you to average between the two. So that's going to be 100 divided by 2, which gives you 50 millimeters. Now don't forget that's going to be converted into meters. Alright, so theta is going to equal the inverse tan of 50 times 10 to the power minus 3 over 0.8. So theta is equal to 3.58 degrees. Don't forget the units. Alright, so we've got a sigma particle goes into a neutron, and you're actually told that it's down strange. Neutron, you should know that off by heart at now. So that's going to be up, down, and x's we don't know. So state whether the particle is a baryon, lepton, or meson. Okay, so what we have here is sigma is a baryon because it actually has the 3 quarks in it. Neutron is also got 3 quarks on it. So if the sigma particle is a baryon, and the neutron is a baryon, then X cannot be a baryon, otherwise baryons aren't conserved, right? Because it just doesn't work out. Now leptons, so leptons are your electrons, etc. Tau, and so let's have a look at the leptons. The sigma is not a lepton, and the neutron is also not a lepton. So that means if X was a if X was a lepton, if it was, then it would have a value of plus or minus 1. Now the lepton numbers wouldn't be conserved because it'd be 0 on this side and plus or minus 1 on there. So therefore that can't be true. So the last one is going to be, it has to be a meson. Alright, determine if particle X is positively charged or negatively charged. Alright, so sigma is up, up, down. So that's going to be minus, so sigma is down, down, strange, which is minus a third, minus a third, minus a third. So that's going to give me minus 1. Now a neutron is obviously going to have a charge of 0, but let's show the working out. So up, down, down, so that's plus 2/3 minus a third minus a third. So that gives me the 0. So therefore x must be equal to minus 1 for the charges to be conserved. Don't forget to put in your reason. Okay, so we're looking at the solar sails. Light bounces off of it and it produces, the change of momentum produces a force and the thing moves. Alright. So what we need to do is derive this equation. And one of the key factors here is that we've got that 2 there. Now where does that 2 come from? So the change in momentum is going to be equal to the final momentum minus the initial momentum. However, the final momentum, or the initial momentum, is going to be equal to the opposite of the final momentum, right, because it's equals opposite in value. So therefore the change in momentum is going to be twice the final momentum. Alrighty. So we've got the 2 covered now. Momentum is equal to h over f, and using the wave equation, c equals wavelength times frequency. We rearrange that. Wavelength is equal to the speed of light divided by the frequency. So momentum is equal to h over lambda, or the wavelength. Now wave equation, c is equal to wavelength times frequency. Rearrange that. Wavelength is equal to c divided by frequency. Let's substitute that back into our equation here. So momentum is equal to h over c divided by frequency. And don't forget the momentum is doubled. We'll chuck that in there. So momentum is equal to, so we got that divided by, so inverse and multiply. So I end up with 2hf over c, which is what we've got over here. Alright, so we've just derived that equation. Let's actually substitute our values in there. So write this in. And most students will, last year made this, the only mistake they really made with this was actually putting it in the calculator correctly and actually calculating the value. So again, watch your data entry. Okay, so what we have here is we've worked out the force that one photon of a particular frequency will actually produce. However, you are shining that many photons per unit time. So with our final answer, we need to multiply the 2 values together. and don't forget the units. Alright, so now that spacecraft is actually going quite fast, so it's now, we've got to show that that's the Lorentz factor. So Lorentz factor is going to be equal to, divided by the square roots of 1 minus, now the velocity is 6 times 10 to the power of 7 squared over the speed of light squared. So the biggest mistake here is students are unable to use the calculator properly and enter it in. So make sure you practice that and use lots of brackets. Lucky last. Now let's have a look at relativity. So travelling it would take 19 years, okay, so that is the frame reference of Earth. Okay, so what we need to do is measure it from the reference point of the spacecraft. Now if you remember, time slows down if you're approaching the speed of light, so we should be expecting an answer less than 19. So it's always good to make a logical check. So you got your time is equal to your Lorentz and the original time. So we'll take, that's times by, so on the other side it's divide by. Let's substitute our values, and that gives us 18.6 years. Please don't go around and changing the years into seconds. Alright, that's it.